Hello everyone. Just give me a few minutes. Okay. Hello everyone. I'm Pushpita Chandan, and this is I'm TA for laser. Am I audible? First, I want to know. You can say that in chat. Um, okay. I am audible. So I'm Pushpita Chanda. I'm a PMRF fellow. I am doing my PhD at IIT Delhi under the University of Queensland and IIT academic program. So I'm a TA for this course. All are enrolled. Laser fundamentals. So as instructed by the Professor Shonai, uh, the first assignment is due. So I will be able to presentation. Okay. Okay, the first assignment is still due, so I am not going to discuss the assignment problems. I will discuss those after the assignment due date has over. So you can give your suggestion what I can discuss. I will keep that in mind in from next classes. As per the instruction, I am briefly discuss what has been discussed in the classes and discuss some problems from some numerical problems. So let us start. And also, please knock me or something if the share slide is not visible, or in some point of the lecture it's not visible at all. First, I'm doing a quick catch up what has been discussed in the class. So What is laser? The full form of laser is light amplification amplification by stimulated emission of radiation. Light, L is from the light. This A is amplification. Is this S stand for stimulation, E stand for emission, and R stand for radiation. Um, I believe all of you know that very precisely. So the laser effect is very much dependent on an interaction between matter and radiation. The interaction they do via electromagnetic waves. So they are. We need to remember when laser action takes place. The there is three kind of radiation involved. One is three kind of radiation in the sense like how the radiation uh, get absorbed or emitted. One is absorption and two type of emission. One is spontaneous and one is stimulated. So absorption is basically most of the time it is stimulated, but emission can be spontaneous and stimulated. So absorption. Absorption. So first, what is an absorption? Uh, like discussed in the class, in every matter there is atoms and molecules. So in atoms there is electrons. So basically electrons are are placed in some discrete energy levels, and there has been various proof about that the electrons are in basically discrete energy levels. And please keep it in mind that these energy levels are not physical levels. They maybe they are physically at same position, the same position, not overlapping position, like they are side by side. One electron may be an E1 state and another is E2 or another is E3, like that. Similarly, if we say the atom is in lower state and another atom is higher state, that doesn't mean that they are physically separated. They are also, they can be placed side by side. So as we say that absorption and radiation, like when some atoms are in the ground state, if there is a radiation falls on them, they absorb the energy of this radiation. We can say radiation or photon, and these atoms absorb that energy h nu and jump to the higher states. that can be, if like if it's a many energy state system, they can jump up to a many states, but that depends on the energy, how much energy it has absorbed. So basic uh, point is, the if when we want a laser action to happen, we give the energy h nu such so that the atoms which are in the ground state, they can go up to a higher level of state. So if it is E1 and it is E2, then H nu should be E2 minus E1. If we give H nu such that it is E2 minus E1, then can only a atom like this red on can jump from E1 to E2. By absorbing this energy, an atom cannot jump from E1 to, let's say it is E3 and this is 4, E3 or E4. It can only jump up to E2. And this is the absorption part. Then comes emission. First, we discuss spontaneous emission. Spontaneous, like I have said, that atom has jumped from E1 to E2 by absorbing the energy H nu. Most of the I will come it later. How can we give that energy H nu? So atom is now at E2 position. So the lifetime of these states are very small. So atom cannot reside in that state so much longer. So eventually it will go back to E1. When it will go back to E1, it will emit energy. And this is spontaneous emission. It is not forced. That is why it called stimulated, not stimulated, it's called spontaneous. So when it do that, it emits a radiation of energy H nu. This absorption most of the time called simulated, because the energy has been given. The atoms are kind of forced from to jump from E1 to E2. And the most important emission, of, without this, the laser action will not happen anyway, is the stimulated emission. So, what is stimulated emission? Stimulated emission is that under the influence of the electromagnetic field of a photon, uh, a frequency nu falls in the higher state of photon, it will go back to the lower state and emit a photon which has same frequency, same phase, same direction, same polarization state. The fact is, the difference between spontaneous emission, that it is spontaneous. No another photon is needed for this transition. But here we need a frequency photon of frequency h nu for this transition. So we need to have a photon of frequency nu to be fall off on the atom which is in energy state E2. So we get another photon of energy H nu. This is called stimulated emission, and laser action depends on this stimulated emission solely. And in the class, Einstein's coefficient has been discussed. So There is a proportionality constant A and B. So A21 says the constant for spontaneous emission, and B21 defines the uh, coefficient for stimulated emission. So we know the number of absorption, and there is another constant B12, and the B12 is associated with the absorption. For laser action to happen, let us assume there is number of atoms per unit volume is N1 in energy state E1 and N2 as energy state E2. N1 B12 into energy spectral density, we can say, is equal to N2 B21 U nu plus A21 N2. This relation needs to be hold. So after some calculation and all that, let me repeat the calculation. It is N2 A21 N1 B12 minus N2 B21, and some simplification, we can write this equation like this. And we already know N1 is equal to N naught into e to the power minus A1 by KT, and N2 is equal to N naught minus E2 by KT. So N1 by A2 is equal to 2 minus E1 by KT. And we have assumed, like in this slide I have already told, that absorption happens when atoms get h nu energy somehow. Basically, this h nu energy can be given by optically, electrically, chemically. Some in any three kind of way it can be given. So it will be h nu by KT. So U nu become A21 B211 e to the power h nu KT B12 B21 minus 1. And we know U nu is equal to h nu cube C cube 1 by e to the power h nu K minus 1. So if we compare 1 and 2, we get B12 1 2 by B21 is equal to 1, and A21 by B21 is equal to 8 pi h nu C cube. So this is the relation between the Einstein coefficients. And there are some like some preferable condition for stimulated emission to happen. So for that we do some population conversion. It is necessary condition for laser action. Thus, in this situation, the number of energy in the higher state is exceeds the lower state energy. Population inversion, very important for laser action to happen. Because basically, the population, say, the population of E1 is N1 and E2, or population N2 is a population of E2. In normal condition, N1 is greater than N2. But for laser action to happen, N1 stimulated emission need to be favored. For stimulated emission, atom we want atom 1 to go to the ground state level. If ground state level is already crowded, no atom will go there. Like stimulation will be there, but we need also environment uh, to also force the stimulated emission. So we need N1 is less than N2. So for that reason we need population inversion, and this thing is called that N1 is less than N2. What we made is population inversion. And another thing, the laser action will be preferred if the energy difference between two state E2 minus E1 is more much more. So there is also a catch. If E2 is greater than E1, much more than greater than, the spontaneous emission will be the largest part. But for laser action to happen, we need a simulated emission. Because in the laser cavity, the resonator, optical resonator, I'm sure this part will be covered in upcoming lectures. This is the mirrors. First, there will be a gain, active medium. Not all frequency will be preferred by this cavity. At each those modes, or you can say frequency mode, and there is a slightly difference between mode and frequency. Slightly, which a huge difference is there, mode and frequency. You can say mode as the kind of pattern, and frequency is frequency. Somehow, what I want to say that not all modes or all frequencies will be accepted by a particular laser resonator. We can make a laser resonator some way that a few frequency will be preferred, and each round trip this frequency will build up and other frequency will cut down, and other frequency that frequency will survive, which frequency at each round trip has gained the amplitude or the energy, and other frequency will lose the amplitude or energy. And this how, when the amplitude or energy or intensity of that particular frequency has reached a particular value, then only that frequency will we will get that frequency as an output. So not all frequencies will be preferred by a particular optical resonator. Yeah, human being can make a laser which give a output of broadband, like delta nu is very large for that thing. Then, like, if it is new, so from nu plus delta nu by 2, nu minus delta nu by 2, the frequency from this to this will be preferred by the resonator, and delta nu can be abroad. But that is not how why lasers are made. Lasers are made to have a particular frequency, and nowadays lasers are used for many kind of application, and for that we need very narrow linewidth, and also we need a laser which has tunability, so that all force lasers to make perfect at frequency, and that, and obviously laser will need some line, that frequency will need some line with delta nu or fwhm. But mode locking is very important for lasers, and we choose gain medium or active medium, whatever we said, like that one frequency or few frequency gain, the amplitude gain at each round trip. So these are some high level discussion, but for your purpose you can keep it in mind that not every frequency is preferred by a laser cavity. So we know that this is like this h nu from this equation 1. We can say that a21 by b12 u nu is equal to the power h nu kt minus 1. So for visible region, h nu is less than greater than kt. So we can assume t 10 to the power 3 Kelvin, and nu like 5 into 10 to the power 14 second inverse. This correspond to lambda 6000 angstrom. Then h nu k t will be 24. So a to b12, we know a21 is associated spontaneous emission, and b21 is stimulated emission. So here we can get a21 by b, sorry, I made some mistake. Although b12 and b21 is same, but for the sake of like logically correct, it should be b21. It will be 10 to the power 24 minus 10 minus 1. Okay, e to the power 24 minus 1, which is 10 to the power 10, which means it is for ordinary light sources, these parameters. So we can clearly see that a21 is greater than b21. So if a21 is greater than b21, then spontaneous emission is much greater than stimulated emissions. But we need for the laser action to happen B21, sorry, we need stimulated emission more. Emission needs to be much greater than spontaneous emission. So for this purpose, B21 needs to be A2. So that's why we choose H nu. Like K is a constant, H is also constant. We can only choose H and nu and T. So for that, choose nu like 3 into 10 to the power 9 second inverse, which is corresponding to lambda 10 centimeter and temperature 300 Kelvin. For ordinary light sources, we know like LED and tungsten lamp and all those, their temperature is at that range. So that's why we have taken T is equal to 10 to the 3 Kelvin. So if we take this consideration, like nu is equal to 300 Kelvin and T is equal to like 3 into 10 to the power 9 second inverse, we get H nu KT is equal to 5 into 10 to the power minus 4. So then EH nu by KT will be e to the power 5 into 10 to the power minus 4. So A21 by B21 U nu will be something E 5 10 to the power minus 4 minus 1, which is 5 into 10 to the power minus 4. So here B21 is greater than A21, which we all need. So now let us discuss some like basic things for the laser part. So there is a kind of laser which gives pulse as an output, like one pulse after some time, second pulse. If it is T1, then after same time of T1, there is another pulse. So 1 by T, this is pulse repetition rate. It's called pulse repetition rate. So for some, like I want to guess, for any laser, if the laser is like safe to use at particular distance, how can we measure the peak power and the intensity? So we need to know some parameters like lambda c or nu c, this pulse repetition rate, average power, and all. Let us see via like example. Let us assume that a laser has pulse repetition rate 50 megahertz and an average power 500 milliwatt. Now, this is one pulse, or you can say that is one pulse. So you can assume it as a triangle. Okay. This is peak power. First, we need to obtain energy per pulse, which is average power by pulse repetition rate. 500 pulse repetition at 50 into the power 6. Okay. I have done the example with 80 megahertz previously. So stick to that calculation. It will be something 6.25 into 10 to the power minus 9 joule. Okay. So that is energy per pulse. Energy is like the area of the pulse. So what is the peak power? And this is delta T, you can say. So for a triangle, it is half into 2 into delta T. If this is delta T, so it will be 2 delta T into peak power is energy per pulse. So peak power into delta T is equal to energy per pulse. So you can write it like EP. So peak power will be EP by delta T. So here we have taken delta T is the pulse width in time duration. A femtosecond pulse, 50 femtosecond pulse. So it will be 50 to 10 to the power minus 15. So we have already got energy per pulse in the nanojoule region, and it is 50 into 10 to the power minus 15. Watt. So it will be 1.25 into 10 to the power 5 watt. Now we want to obtain the intensity. So intensity is power by area. So, and what area we are talking about? We are talking about the cross section, the laser output. The laser output is basically, we can say, when we put a paper in front of a laser, most of the time it's TEM00 mode. So it is basically TEM00 mode is a kind of circle. So area will be pi r square, and the r is the radius. So if we assume that we are talking about 2 centimeter diameter cross section, then for this example, intensity will be 1.25 into 10 to the power 5 watt pi into 0.01 whole square to be 4 into 10 to the power 9 watt per meter square. Now remember, from intensity we can go to electric field, magnitude of the electric field. So we can say that EP is equal to 2 IP epsilon naught C, which is almost 1.7 into 10 to the power 6 volt per meter. Okay. So if we compare this with a physical system, like one on here there is nucleus, an electron is moving around this RV distance, which is called Bohr radius.
Ma'am,
Yes.
can I ask you a question that if the contents taken on Friday and Saturday live sessions are they same?
The what content? You are
Yeah,
asking about content.
like weekly we have two live sessions, right?
Yes. For the first session, I haven't discussed. I have not a discussion with Bhaskar, but from now on, I think there will be a discussion, because I have discussed with Professor Senoy what should I discuss in this class. He asked me that just briefly discuss what have been taught in the lectures uploaded, and a small numerical things regarding lasers. So the example now I'm discussing it, this kind of question appears most of the time, not in a simple language like this. You will be given a very tremendous and complicated diagram, and then you will be given these values in between, so you need to figure it out, and the mathematics is very simple. That's why I'm discussing this example, and after that I will discuss some other examples like that. So
So in
I am not
coming
sure.
weeks,
I am
the
not
session.
sure that what has Bhaskar taught yesterday. Yeah, yeah.
So
Coming session, I guess. I will also talk with Professor Shanoy and
I'm
let you
just
know.
asking if the Saturday and Friday sessions are same. Is it okay if I just attend only one?
It's up to you. And also, these sessions will be also uploaded in YouTube. So if you
Okay.
don't want to attend live session, you can also always go back and watch those things.
Okay, fine, fine.
Yeah. For this week, I don't know what he has taught, so I cannot say the content is same or not. I hope
Oh,
you understand that.
yes, yes.
Yeah. So we can compare the laser electric field or peak power intensity with some physical system. So this is an atom, simplest atom you can say. The electric field magnitude, we are always talking about magnitude here. You can say. So this value will come 3.2 into 10 to the power 10 volt per meter. So we can see that laser field was of the water of 10 to the power 6 volt per meter. Here, the electric field between an electron at RV distance, well, you can say it is a only one positive uh, element there. So it is out of the order of 10 to the power 10 volt per meter. So laser field is far less than that, but somehow the lasers are made like that. We get power intensity power are much more greater than that. Now we can discuss. Okay, presentation one. Um, Now we can discuss some other questions like so I want to discuss something about yeah. There is something two level laser system where lasing action took place between these two levels, 1 and E2, that via pump these atoms are like jump from E1 to E2 and there is stimulated emission and we get lasing action. But this two level system is not good for laser action. And the reason is that a steady state population inversion cannot be achieved by this. This is the reason. So we need a three level laser system. So here this the diagram, energy diagram of three level laser system I am drawing. That is N1, N2 and N3. This is E1, this is E3, this is E2, and we give a push via pump which can be seen as H nu P. So the molecules from E1 jump to E3. So we choose that energy state such a way that the relaxation from level 3 to level 2 is very fast, that the atoms relax down to level 2 very fastly. Its lifetime is very low. Now laser action happen when the atoms from N2 jump to N1. The stimulated emission happens between these two level. So the laser action happen now. We are, but here is also a problem with like 3 level laser. So we need to go to 4 level laser system. So because of what happened there. There is some glitch. I'm sorry. Okay. Okay. So uh we need to go to 4 level laser system because population inversion has been like achieved, but one has to lift more than 50% of the atoms in the ground level in order to obtain population inversion. So, so we need 4 level laser. So the laser action had been achieved in 3 level laser, but the ground there the pump has to be more efficient for the 3 level laser. It's more efficient or more working, because we cannot have ground level the lower level of the lasing level as a ground level. So we need 4 level laser system. Here the particles has been pumped from E1 to E4. Then particles quickly decay from N4 to N3, and this is the lasing states between N3 and N2. This is reverse laser. And when the particles came to N2, so N2 has been chosen like that the particles are very quickly decay to N1, but only the reaction only happen between N3 and N2. Sorry. 3 and N2. So there come a question in net JRF, net CSR, net in some years from this laser action, the lifetime and which which state will decay, atoms in which state will decay first. Please go through that kind of question. It's few like few lines or a few logical reasoning. uh, it's nothing that complicated. So just go through it, and it will be that simple. Let's think logically that which states need to be greater lifetime, or which state is don't need that greater lifetime. So I cannot discuss the assignment this week. So I thought I need to discuss some other thing. Let me give some time, and I will discuss something. Decided this thing that provided the fractional question would be ordinality, there was a question, production, operation, problems, body problem, stream profession, and ordinal mechanism. Okay.
Can please explain the model questions of first assignment?
What? I cannot get your point. Explain the modal.
Model assignment questions, problems, madam.
Okay, I'm not allowed to like explain those questions till now. I will I will discuss those things after you submit the assignment. After that, I will discuss those things.
Okay, okay. I'm
That's
not
why I'm
understand that concept. Ln of n1 by n2 model question.
model question like assignment,
Ln,
like those questions.
ln.
Can you show me the question?
Okay, just wait a minute, madam.
Like I cannot see it. Okay,
Okay,
pin it. You can share. You can share. Uh, I will like unshare my slides. You can share that point.
madam.
Okay. Okay.
In the above two-level atomic system of n1 is the number of density of atoms in the first level and n2 that in this. In the second level, then the value of ln of n1 by n2 at room temperature.
There is no other like uh, information given with about that.
Not there, madam.
Uh, it's an
Question.
question.
Question and ninth question also I don't understand.
Okay, in the above two-level atomic system, so the hint is the question number 7. You need to like have yes in the question in the yes you already solved there. You need I can give you hint only. I cannot like solve it for you for now. Okay, I can only give you hint. Like and then n1 is equal to n0 e to the power. I have already mentioned that thing, right? I can I can't give you the thing clearly. Can you see the screen? Oh, okay, sorry. Uh, can you see this? N1, you can say that N1 is equal to N0 e to the power minus E1 kt, and N2 is N0 e to the power minus E2 kt, and N1 by N2 is this. And I have already mentioned that H and K is a constant. Only variable thing is nu and T. So in your question, you need to find nu and T, and it is given there. Only that much I can say you that nu and T is given. Just think about it, and it's very easy. You can do it. Otherwise, I will solve those things next week.
Okay.
I hope you have understand what you need to like put. Actually, that's the constraint I was given, that I cannot discuss the assignment question. That's why I'm mm, searching for question. Give me a few minutes. I will discuss some questions with you. Continue. So spectral. Okay. Hmm. Hmm.
When will this class be available on YouTube?
What?
When will these classes be available on YouTube?
I cannot understand what you are saying. Like, please say it slowly. When is the class?
When will these classes be uploaded in YouTube?
Okay, like as soon as I the class has been recording already. So the file size is very big. So
Okay.
I live in hostel. So whenever I get that speed, I'll upload it as soon as I finish this. It's okay. So I got some questions, but for that I need to introduce some more parameter. If it is okay with you, I can continue with these questions. Okay. Okay. So we know this Einstein's parameters A21, B12, and B21. Right. So there is a parameter TSP, which is 1 by A21. So what is TSP? It is called spontaneous lifetime associated, like it is called spontaneous lifetime, but it is associated with the transition between 2 to 1. Okay. So in hydrogen atom, there is a transition question. It is kind of question. 2p to 1s. Okay. So the lifetime is given 1.6 into 10 to the power minus 9 second. So you need to obtain the frequency of the the frequency of the transition is also given. Frequency is omega 1.55. Okay. 1.55 into 10 to the power 16 second inverse. Okay, it's omega. not new. Okay, keep that in mind. So the question is, what is B21? So you are given TSP and you are given omega. So what is B21? So it is very like, from we know A21 by B21 is 8 by H nu cube C cube, and TSP is 1 by A21. So we need to convert mu to nu and H to H cut. So the thing will be like pi square C cube. Okay, sorry. Pi square C cube H cut omega cube N naught cube. Okay, here we like the from the book I have been like solving the question. They have like accounted that refractive index portion in all the equation, and in actual calculation of lasers, refractive index is also been like considered. But for the sake of simplicity, you can like put in naught is equal to 1, so it will be 1, so it will become h cut omega cube pi square c cube. So when you put B21 will be pi square c cube h cut omega naught cube. So here you put omega or omega naught, whatever you can put, like the frequency you are given, into A21. A21 is 1 by TSP. When you put all this value, you get B21, which is 4.1 into 10 to the power 22. Okay. And also you can see the system will have like, okay, delete. System will have what I say, spontaneous emission. Spontaneous emission.
Not visible, madam.
Okay, screen not visible. Oh, sorry. Thank you for mentioning it. Okay. Is it visible now?
Yes, madam.
Oh, have you did you see those slides?
Yeah, madam.
Yeah, okay. Okay. Cool. So yeah, the extension of question can be if the system will give spontaneous emission or stimulated emission. Okay, this is not a big deal because it is another line. We have already have the value of B21. So A21 is 1 by TSP. So we know that what is the TSP of this emission. So it will be 1 by 1.6 into 10 to the power minus 9. So it is 6 into 10 to the power 8 second inverse. So A21 is of the order of 10 to the power 8 and B21 is of the order of 10 to the power 20. So we can say that delete, yes, new slide, that A21 is less than B21, so there will be stimulated emission. So one thing I want you to notice that TSP is given in the unit second. So 1 to 1 is a unit, has unit of second inverse, but B21 doesn't have the unit of second inverse, right? They are not unitless property coefficient A21 and B21. B21 is what? 1 to 1 by 8 pi h nu cube, and here it is c cube. So A21 is second inverse, c cube is meter per second whole cube, h have unit of joule to second, nu frequency in second inverse whole cube. So after all this simplification, B2 has a unit meter cube by joule into second square. So I understand it's basic laser fundamentals, but these are small things like the unit of A21 and unit of B21. You can it is very easy to for you to calculate, and please keep it in mind that A21 and B21 doesn't have like they are not unitless. They has unit. Mm. Another questions like okay, the following characteristics not lambda not by delta lambda function present in population gain. Okay, and there is another coefficient, gain coefficient. Okay, so please remember those things I am discussing, like the lifetime of stimulated emission. Here I have spontaneous lifetime. No, also the I have mentioned only that TSP is 1 by 1 to 1. It is mathematical thing, but what is TSP? Okay, let me tell you that TSP is the time the population of level 2 reduces by 1 by eth in time, like the time population reduces to 1 by eth of initial time. For state 2. So similarly there is the TSP is a new coefficient. There is another coefficient, a gain coefficient. As I have mentioned briefly, I understand that like it is slightly like outside the scope of the lectures, that each modes need to be gain. It cannot lose its intensity or emission. So there is a gain coefficient then the gain coefficient need to be plus, that is alpha. So alpha is equal to pi square c square omega naught square n naught square tsp. That is, and into g omega. G omega describes the intensity profile of the laser, or frequency profile, you can say. You can replace it by delta omega n1 minus n2. So whenever any question will be given, you need to like only remember alpha. Everything will be given, the every parameter will be given there. So there is a comma. So in a question, it is mentioned that n0 is equal to 1.76. TSP is equal to 3 into 10 to the power minus 3 second. Lambda naught is equal to 6943 angstrom. It is given g omega naught is equal to 1 by delta gamma if, into 1.1 into 10 to the power minus 12 second. So here the question is that is there will be a laser action or not. So we need to obtain the alpha. If we put together that n naught is given, tsp is given, g omega or delta omega is given, n2 minus n1 minus n2, that thing will also be given, or it will be mentioned like for ruby laser or another kind of laser. For ruby laser, n1 minus n2 is of the order of 10 to the power 19, or you can say it is 1.5 or 1.6 into 10 to the power 19, but if you can only remember 10 to the power 10, it's okay. Or they will say that the temperature or the frequency. So we already know n1 by n2 or n1 by n2 formula, E by 8 e to the power h nu by kt. Okay, this is n1 by n2. You are given lambda and temperature at thermal equilibrium temperature. You can like assume 300 Kelvin, which is room temperature. You can get n1 by n2. Okay, from there you can like produce which is what is n1 minus n2. So you can like get, I'm not doing this explicitly because there is a question similar to this in the assignment. Otherwise I will do the question step by step. I'm going to give you just hint that the approach of like attempting this kind of question, you need to know just another equation, which is gain medium and gain coefficient, nothing else, nothing new is there. Like in previous example question, that it has been stated that there is a transition between 2p and 1s, but this is like extra information. It doesn't matter it is a transition between 2p and 1s or not. Like that tsp is given and omega is given. This is the only thing that matters in the question, nothing else. Similarly here, if you know the gain coefficient, expression of the gain coefficient, which has been like I have mentioned here, and if you like here also that pi and c, you know that g omega is like the frequency profile of that laser, that is most of the time delta omega. So that will be also given. The line width, it will be given as a line width or normalized line shape function like this. So you need to like put omega and tsp, and n1 and n2 I have give you the hint that n1 by n2 is that h nu by kt. From there you can get n1 by n2, n1 minus n2 also. You could have some additional information, and for most of the cases n naught if is not given, then you can consider it is 1. So if you put those things, you can get that gain coefficient. Okay, and once you gain the gain coefficient, you know whether the system will work or not. It is for ruby laser. For another example, they can give you anti-wag laser. For that, they will be given n naught, tsp, lambda naught, and all those things. And somehow they can also give you the alpha thing, and you could have like you they can ask you that what is n2 minus n1, and from that they can ask that how much of the population like is bigger in n1 than n2. So this kind of question can be asked. And another, there is a threshold condition expression, and let me tell you the threshold condition. It appears over a broad frequency range. When you look to me like comma, and then alpha is never being is amplified. The comma. That will be favorable. Okay. The threshold condition, in a threshold condition is n2 minus n1 is must be greater than 4 nu square n naught cube c cube tsp by tc into 1 by g omega. Okay, so the tc is given by, okay, this is the threshold condition, and 1 by tc is given by c 2d n naught to alpha 1d minus ln r1 and r2. I'll explain each term. So there is a term tc, another term d, and another is r1 and r2. Okay. So D is basically, if a optical resonator is been considered, it is an optical resonator. There is a gain medium is also be placed. So the distance between those two mirror is D, and R1 is the radius of curvature of mirror 1, and R2 is the radius of curvature of mirror 2, or sometimes they are called reflectivities, not activities of mirror 1. Okay, it is safe to like say this as reflectivities, because there is a certain relation between the like curvature and the reflectivities, but the relation is a bit complicated. And R2 is a reflectivity of mirror 2, and you have also seen the D, and the term for TC is critical temperature, so reduces threshold population and corresponding to okay. So the next question will be if a laser is given 6943 angstrom, spontaneous emission lifetime is 3 into 10 to the power minus 3 second, and n naught is equal to 1.76, D is equal to 5 centimeter, R1 and R2 is equal to 0.9, alpha is almost equal to 0. So what will be the like n1 minus n2 minus n1? So for that you need to like first calculate TC, which is 2d n naught by C 2 into alpha 1 D minus ln R1 by R2. So there will be a value of that. So you can like calculate n2 minus n1. So TC will be 2.8 into 10 to the power 2.8 into 10 to the power minus 9 second, and then 2 minus n1 will be 1.5 into 10 to the power 17 centimeter minus cube. A similar question is like that, that for helium neon laser, lambda naught is given, TSP is given, N naught is given, D is given, R1 is equal to R2 is given, alpha 1 is given, delta nu is given, and also G omega naught also given. So you need to find TC and N2 minus N1. So all like previous example, same thing, the Armstrong spontaneous equivalent lifetime second inverse 10 to the power minus second. Let me put it clearly. Here 10 SP is equal to 10 to the power minus 7 second. N naught is equal to 1. D is equal to 20 centimeter. R1 and R2 is 0.98. Alpha 1 is almost 0 here. Delta unit. Delta nu was given 10 to the power 9 hertz. So from that you can like obtain the omega naught, which is 1 by delta omega, well, 1 by 2 pi delta nu. It is equal to 0.16 into 116 into 10 to the power minus 9 second. So now we can calculate TC, which will be 3.3 into 10 to the power minus 8 second. And from that we can see N2 minus N1 is 6.24 into 10 to the power 8 centimeter minus cube. So from these two example, you can compare that when R1, R2 was, yes, I understand that other parameters also changed, 0.9, and TSP was of the order of 10 to the power is of the order of 10 to the power minus 3 second, that N2 minus N1 is of the order of 10 to the power 17. But when R1, R2 0.98 and TSP is of the order of 10 to the power minus 7 second, like very quickly, the lifetime of the spontaneous emission is very quick, then N2 minus N1 is of the order of 10 to the power 8 meter cube, and this is centimeter cube. So we can say that it is for say it is for laser 1 and this is for laser 2. If we change the reflectivity or the spontaneous emission time and other things are like almost like comparable, and the distance also, I have like here distance is 5 centimeter, here distance is 20 centimeter. So that affects the like the how much population inversion is needed. Into population inversion is like N2 must be greater than N1. How much greater it needed, that these parameters like spontaneous emission, reflectivity of the mirrors, and the distance between mirrors, they control those parameters. And also from this equation, like TC 2D and N naught by C to alpha 1D minus ln R1 R2, and what is n2 minus n1 is greater than this value. From that value, we can, that from this equation, we can see that to be able to have a population conversion, TC should be large, so that the cavity loss must be small. Hello? Okay, voice is not clear. Am I audible now? Yeah. Okay. So we understand that n2 minus n1 must be greater than this value. So TSP should that threshold inversion, for better threshold inversion, smaller values of TSP TSP is great, because here also in the example we can see that 10 to the power minus 3 corresponds to n2 minus n1 is the order of 10 to the power 17. I understand there is also another parameters, but TSP has a role, and for TSP 10 to the power minus 7, it is 10 to the power 8. So these parameters affect the n2 minus n1 value or threshold population inversion. Light. And there is some there's another topic, coherence. So it will be like discussed in a very broad manner later, but coherence, there is time called coherence time, which is 1 by delta nu. So this delta nu is the line width of the pulse, this delta nu, or you can say that whether it is line width or monochromaticity. And another, this is coherence time, and this is another parameter is coherence length, which is C time TC. So these two parameters is also important for to laser action happen. Coherence time, there should be a large coherence time and large coherence length. Ideal laser have infinite coherence length, but that is not possible. So the more the coherence length is there, the laser better the laser action, and more coherence length, it means more coherence time. It means delta nu must be the small. That's why like we always prefer for the laser action, laser pulse, to be delta nu tends to 0. It cannot be 0. Delta nu cannot be equal to 0 because quantum mechanics prohibit us that. But we want all tends to 0 or very less FWHM. Also, there are different things like if it is like intensity, and this is in lambda, and in like wavelength, intensity varies as a Gaussian. But when we convert it into a frequency domain, it will not be Gaussian. It will shift it towards left or right something, because delta mu is C by lambda square delta lambda. Always remember, if in frequency domain, if it is Gaussian, so if frequency spectrum is Gaussian, then wavelength spectrum is not going to be Gaussian. There will be a shift towards left and right. because of this relation. Okay, other things. And some things you need to be remember that the separation between D1 and D2 lines, it is almost 6 angstrom. And what are the like property of a laser, which is high and which is low? Like body radiation. And another thing, like you need, okay, it is a course on laser, but if you want go through few pages extra, you can go to any quantum mechanical book and see the Planck's radiation distribution and how the calculations are, and what is the difference between Planck's Wien's distribution and Rayleigh's distribution, and how that when the temperature varies, how the peak varies. And that's all of like even this TC uh, TC expression, and okay, I have mentioned the TC expression here, and N2 minus N1 expression, that are a bit higher level of expressions. And if you want to go through this thing, the chapter 4 of the Tyagarajan and Ghatak, like I have gone through those examples only. You can go through those part, and you don't need to go through all of the part, but a few things like this, like what is, it is a very basic, the spontaneous emulation lifetime, or like here I have mentioned what is TSP, uh, spontaneous emission lifetime, or the time population reduces to 1/8 of initial time. So this is a very basic things, and there is nothing like you can skip the calculations part, or the calculations they have done, but you can like understand what is that significance of alpha and gamma in the laser action. Okay, that's all for my side for today. The next week I will be able to discuss the assignment questions, but the question number 8, I think you will be able to do that, because already I have given you the hint, and I think that is enough for you to able to do that, because you have already done the question number 7. Okay, if anyone have any uh, what I may anyone have any question, you can post that on the feedback, okay, forum in the NPTL. I will try to solve that in the next class. Thank you.
Thank you, ma'am.
Okay.